Thanks for coming to the seminar. We're delighted today to have Uzy Smilansky, who will tell us about graph and chaos theories combined to address quantum information. So thank you, Uzy. The floor is yours.
Thank you very much for inviting me. Of all the words which appear on the title, I think the important one is chaos. And I believe that all of you have heard about chaos from the butterfly, story that the butterfly starts somewhere and then it propagates all the way all around. As far as I'm concerned, the butterfly problem is translated into proper classical mechanics is a concept which involves something which is called the Lyapunov exponent. And the Lyapunov exponent measures the rate by which two trajectories, which starts to be one next to the other, are separating in phase space. Not in coordinate space, but in phase space. And the problem then is how to relate what we start with, that is a quantum system, which is described by Hamiltonian, by a matrix, which is a Hermitian, n by n matrix, or v by v, it will be called later. And then how such a quantum object, which does not live in phase space, it believes, there is this principle that delta x times delta p is the Heisenberg principle. You are not allowed to specify both position and momentum together. How can we draw quantum mechanical problem into giving us a purely classical property, namely Lyapunov exponent? That is the aim of the story here, and I will go through the. I cannot show anything there. So you see the train, which starts in the quantum world and will lead us very slowly into the classical. Now, I know that you are not, I assume that there are many people here who know. Sorry, I forgot to switch off my telephone. So it is, not many of you are familiar with graph theory, with quantum chaos. So I will do it on a very, very elementary level. And please stop me whenever you don't understand. I am not going to show you all the story. So what I'm going to do? What is the problem? I told you what is the problem. How to define chaos or the Lyapunov exponent in the quantum, which corresponds to the quantum world. The second part, because I'm going to use graph theory, it will be an introduction to pedestrians about graphs. Then I'll show how the Lyapunov exponent for a quantum Hamiltonian given as a matrix is defined. And then I will give you some theory, ergodic theory, and show you some results which are numerically supported by all kinds of estimates and approximations. So stop me either by the time or by your questions. So what are the graphs? Well, you see a graph. It is a set of vertices, red points, which have something which is called connection. So they are connected somehow. You don't know it, but there is a connection. In a family which have several mothers and one father, the brothers which belong to the same mother are connected strongly, but the ones which are connected, which have a different mother, are less strongly connected. So the graph is something which tells you how connected things are. And then, so in this representation of the graph, we also mark, you see on the right-hand side, this is a special vertex, and then you see that all the connected elements are called the star of this vertex. So this is more the star, the vertices which are connected to a given vertex. Now, there are two ways to think of a graph. The standard way to think of a graph is by defining the connectivity between the vertices by a matrix A, which has the values, which has the index of the vertex, and it is 1 if two vertices are connected, and 0 otherwise. Because of this definition, it is a symmetric matrix, and we exclude self-connections. So I don't want a brother to be a brother of himself. Now, the number of elements in a star, or which are connected to a vertex V, is called a degree, and I marked it, I denoted by D sub V. Now, in the quantum, or in the theory of graphs, one considers a space of vectors of the length capital V, the same number, and associate with each vertex a function or an amplitude or whatever you call it. And the Hamiltonian, which describes the dynamics, the quantum dynamics on this graph, is essentially the Laplacian, which is minus A. So it is given in terms of the connectivity and also counting the number of edges. Now, this is a very simple example. This is a graph. You see there are vertices and they are connected. And here, the matrix A is tridiagonal because there is every point is connected either to its right member or the left member. And therefore, the A is a tridiagonal matrix. And you can write the Hamiltonian of this problem like minus A, the Laplacian, plus a potential, if you wish. So this is the quantum dynamics to which we would like to start. We have a vector, you have an operator, a matrix H. There is a space of vectors psi where this matrix operates. You want either to describe its spectrum or the dynamic which is induced by just looking at e to the minus iht and looking at how a space is evolving in time. And this is configuration space. But now we can also look what is the corresponding phase space. So remember that each edge is defined by two vertices, where you start and where you go to. If you think about it this way, where you start and where you go to, it's like having the position and the velocity. Because what is the velocity? It is where will you live after a time delta t. So phase space, mechanical phase space, is essentially translated to this discrete space by the edges. Now there are much more edges than there are vertices, because in each vertex there are many coming out. And then I will define also the edge. I will, you see, you can read it. I cannot point on it. An edge will be defined by the two vertices with which I start and I end, and the edge with a hat will be the reverse direction, involving the same vertices, and it is different. The edges are directed edges. This is the momentum. And then you can also write a connectivity matrix for this particular representation by writing this is C, which you started an edge E prime and E, and it is 1 if the origin of E is equal to the terminal of E prime, this is the tau and the O, and 0 otherwise. So if they are connected, if one connects to the other in the same direction, I mean, the ending of the one is the starting of the other. Then it is this is a matrix, and it has a dimension of twice the number of degrees of the vertices. So this is now the new space. Now, those of you who remember classical mechanics, remember that the phase space is a space of two functions per time. It is the momentum and independent the position. Whereas configuration is only x of t. So this corresponds to this. This is the discrete analog. So what we did was to go from the vertices to the directed edges in the dimensions. So here is a classical billiard, it is called. You see a ball which goes along, scatters from the walls. And if you give the position on the boundary, then you have the configuration space. If you add to it the angle, then you can know where it will go to. And this is necessary, and this is called the Poincaré map of classical mechanics. So the entire mechanics can be described in terms of points on the boundary and the angle to the tangent. And then the rest will be reflections. So at each point there will be a reflection. So you should know where you reflect from and what angle you reflect. This is given to you. So this is called Poincaré map. Okay, now the question is how to turn this information, our original Hamiltonian matrix, which was in dimension capital V, to a representation in edge space, in the phase space, sorry. So in order to do it, I will show it to you only for a matrix which is zeros and ones, so only for the adjacency matrix and its spectrum, whatever you want. And then I will say something about general matrices, but I will not prove anything. So suppose that we have a vertex V, which is in blue here, and I have the outgoing edges and the incoming edges. Now suppose that for every one of them, I require that the wave function, the original wave function or the original component phi omega can be expressed in terms of two amplitudes which correspond to the two directions on the edge which connects omega and V. And V is the other vertex, which is the center of all these vertices. And this is a legitimate writing because I express two variables in terms of two other variables, so it's fine. However, in order to have a consistent description, we have to, I call the amplitudes which are written here, I call outgoing or incoming, depending if you are coming or outgoing from V. And in order to get a completely picture, I have to that phi V is uniquely defined. V is the vertex from which everything is going out. So in all this, the phi V is well defined. This gives D-1 conditions. And the other one, we want that the phi's are eigenvectors of the Hamiltonian, which is in our case A and D. So we require this number 2. And these two requirements sufficient to define for each vertex a scattering matrix, which I call sigma of V. And it is a function of lambda because number 2 depends on lambda on the spectral parameter. And then the vector of amplitudes incoming on the right, if they are multiplied by sigma, then you get the eigenvalues on the left. So this defines to you a scattering problem on the graph, because each vertex now is a scattering center. There are fluxes which are coming in and fluxes which are going out. Because this is how it took me a long while to find what is the most convenient way of doing it. And because of the symmetry and complex whatever, I thought that this is by the way something which I did at 2007 here. So you see. But at any rate, so we got into the point that we have, for every vertex, we have a little matrix, a scattering matrix sigma v, which relates incoming and outgoing amplitude. Now we can put them, so this is called it is the junction of, if you wish to call it in physics, junction scattering matrix. And you can write it explicitly, it doesn't matter, but you can write it explicitly, it's written here. So now what we do is to take each of the sigma, here is one of the left, on the left hand side there is sigma of the vertex v, and combine them for the entire graph. So at each vertex we put this scattering matrix, and this gives us the matrix sigma. So the matrix sigma is a square diagonal, so diagonal, there are squares of diagonal, and each of the elements, each of the squares is a matrix as is written on the left hand side, and this describes, if you wish, the scattering. But now we have to remember something. Yes, sir.
So you somehow calculate scattering matrix, but to like this junction, there may be infinite remaining scattering matrices, right?
Yes, they are all on the diagonal here. It is not the end. Now I'm building up the.
So you haven't.
Just a second, and you'll have an answer. Now you see, what is confusing here, that the same edge, directed edge, can be thought of as going from A to B as an outgoing one, or an incoming from B. So if you want to define consistently your matrix, you have to introduce a permutation, and this permutation which does this transformation for you. And then this is done here by the matrix T. In matrix T, what it does, it is just exchanging on one side the outgoing into incoming. So every time that you are doing a step, you are outgoing from one, but you are incoming to another. So when you multiply such matrices, because you want to know the evolution, that you have to remember that. And that gives you the matrix U, which is a unitary operator. This can be easily proved. And it has this property that connects incoming to outgoing and outgoing to incoming. Now theorem. This is really a theorem, but I'm not going to prove it. That if you look at the determinant of the matrix U, which is defined here, of lambda, the matrices are defined are functions of the spectral parameter, minus the identity of dimension D, then the spectrum satisfies that this determinant is equal to 0 if and only if you are on the spectrum of H. Or the spectrum of, in our case, it is the spectrum of A of the connectivity matrix. This is a theorem. So now what we replaced was a matrix H, which is a Hermitian, with a unitary matrix. Because now we can think of the dynamics as defined as going from edge to edge to edge with some probabilities, and the probabilities are given by the matrix U. You have an amplitude to go from one to another. Take the square of the amplitude, you get the probability. So this is it. And then you can also write a vector of amplitudes by which you start and which you normalize. So its length is equal to 1. And then if you just operate the matrix U t times, then after t times, A of t is equal to U lambda by t. Because U is unitary, then you preserve the probability. You preserve the sum of probabilities. So probability is preserved. Now, has anybody of you learned about the semi-classical approximation? What is the relation between rays and rays, you know, in geometrical optics, to waves in wave optics? Well, in geometrical optics, we consider the lines. And the waves are a front, because they are front of electromagnetic radiation. But the front is characterized by this line. And we can have interferences because waves interfere. So the classical approximation, or semi-classical approximation, tells you the following, that take your wave picture, associate with each wave it's as a direction, so it is just where you come from and where you go to, and forget about interferences. Just take the scattering as if it is a scattering in a billiard table. In a billiard table, you don't have a phase. So that is what we do here. And this is how it is done formally. Here is the plane wave coming, scattered from these circles. So it comes at theta I and goes to theta f. The semi-classical approximation is to count all the scattering trajectories which go from this initial angle to this final f. And this is done, this is written here. And then all the interferences you just throw out. So what remains is a probability, the classical probability. So this is the definition of the classical probability, and that brings us from the quantum world to the classical world. This classical approach. So everything which I told you so far was exact. No precise, no approximation, nothing. Here is a state where I say I drop the quantum effects which correspond to interference. Everything else is, the matrix elements of sigma are quantum, but everything else I drop, and this is the approximation. Now, if you say it is not enough, you are right. Question, do you get something out of it? You get a lot out of it. So, before we had this, when we were speaking about the quantum problem, or the wave problem, we spoke about so now we are coming to go from the distribution in terms of waves to distribution in terms of edges and directed edges. And the discrete Poincare map is exactly the map by which you give edge to an edge to an edge to an edge. It's like position velocity, position velocity, position velocity, like in the classical dynamics. Now this matrix has the property that it preserves the amplitude square, which means it preserves the probabilities, and it is so this matrix, which I write here, the pi, you see the pi is the probability to go from E prime to E. It is the absolute value squared of the corresponding matrix element, S matrix element. S matrix element, because it is unitary, sum to 1. So the probabilities sum to 1. So, and then the matrix that you build out of this, it is it is written in terms of the absolute value of the unitary evolution u lambda squared, and this is b e prime eb. And I'll just show you how this is done for a very simple problem. Here you have the triangle. It has 3 vertices, and it has C directed edges. You can write the scattering matrices from each of the of the circle, so of the vertices, it is 2 by 2 because there are 2 edges coming into 2 edges and incoming and 2 edges outgoing, so it is 2 by 2. It is, of course, preserves probability, so the reflection probability plus the transmission probability is equal to 1 because you can either reflect or transmit. And then the matrix pi, which was defined before as the matrix element squared in these squares, as you can see on the left, if you multiply this time, the permutation, which brings you an outgoing to an incoming and so back, it gives you the matrix B. The matrix B is a very important matrix. This is what we shall use. And it is a B stochastic matrix because the sum of the elements is equal to 1. The sum of the rows is equal to 1. The elements are positive because the probabilities, transmission probabilities are positive. And the spectrum of B is, because of the Perron-Frobenius theorem, the spectrum is inside the unit circle in the complex plane, and 1 is always an eigenvalue, -1 time sometimes. But 1 is always a single eigenvalue, which always occurs. And the corresponding eigenvector is the unit 1, 1, 1, 1, 1 divided by the square root of the number. Yes? Of which? Is transition probabilities. Of B or of the B? It is the transition probabilities. You go, what is the, you take the quantum transition amplitude, which is sigma. You square sigma, you get the probability classical to go from edge 1 to edge 2. That's it. So it is transition probability. And the idea is the following. Suppose that you start with a certain distribution of probabilities, and you want to see how it evolves. So you take the matrix B, you multiply once and twice and as many times as you want. And then what happens is that because 1 is the largest eigenvalue, asymptotically, every initial state will go to 1, 1, 1, 1, because all the other eigenvalues are less than 1 because they are in the unit circle. And therefore, what you get finally is the completely mixed state. Okay? So this evolution guarantees that you go into the mixed state. 1, 1, 1, 1, 1, 1. And the rate by which you get there is related to the butterfly. This is our butterfly. Okay, did you get it? Am I too fast? Now, this, what I showed you, was specific and simple relatively to a matrix A, which is 0, 1, the adjacency. The question is, what do you do if you have a matrix which is not 1 and zeros, which is any matrix that you just can imagine, which is Hermitian, that's all. Can be complex, can be real, but it is Hermitian. And then we have a theory which tells you how to build the corresponding evolution operator to as we did for this. What we do is we associate with each matrix H given to me. You give me matrix H. I choose all the vertices, or all the pairs of vertices, I and J, for which the Hamilton operator, this matrix, is not equal to 0. I associate with it the value 1. If Hij is equal to 0, it is 0. And then what I get is a matrix A of the same kind as before, which is connectivity. Two vertices are connected if the H is not 0. And then this defines the graph. But what changes is the Laplacian. The Laplacian depends on age. Now I'm not going to tell you the story. It is complicated. It's mathematics. It is not even mathematics. It is computational. So what can do is to write this the matrix U of E. E is now the energy, and then where am I? Yes, and then again, if you have this Hamiltonian, this general matrix H, its spectrum satisfies the equation determinant of U of E minus I equals to 0. So the secular equation, or the secular condition, replaces determinant of H minus IE equals to 0. It is replaced by determinant of U of E minus I in a different dimension equals to 0. So now you could build a lot of nonsense around it. For example, suppose that you want to count how many eigenvalues you have up to a certain value, the number counting function, the spectral counting function. Then you use Cauchy theorem, and then you take the logarithm of the determinant of U, minus 1, and then you expand it, and you get the exact result, which gives you a trace formula. A trace formula is a formula. Do you know what is a trace formula? So it is, the trace formula is expressed in terms of something which is a smooth function, r cosinus H minus lambda square root, never mind, plus a sum over periodic orbits. And the periodic orbits have amplitudes. Now, in order to show you, sorry? And the amplitudes are easily calculated, or I mean explicitly calculated, and it is written in terms of the little matrix sigma. And here I give you, because as a physicist, I don't believe in proofs. I believe in numerics. This is only to wake you up. And then you see the black line, I hope you see the black line, is the actual number counting function for a certain matrix. So every time it is a 30 by 30 matrix, I believe, yes, 20 by 20 matrix, and you see that it starts low, down low in the energy. This is the lower axis is the energy axis. It starts on the 0 axis. There are no states below a certain given initial state. And then it shoots up by a staircase. Every time that you meet a spectral point, you go up a stair. And then it ends up at 30, the black line. Now, the red line, the black one is the numerical result. The blue one is the smooth part. It is the first term. The green is when you add periodic orbits of length 2. Periodics of length 2, what are they? How do they look on a graph? Beautiful. Come to me, you'll get a cake at the end. And then what you see is that it does a very nice job. It's almost precise on the interesting line, and then it misses the 1. Okay, so you add another one, p equals 3. What are the periodic orbits which are 3 and not U? What are triangles? Amazing. You also come to cake. But then they don't make any good correction, and then you add also the 4. And you see that there is an improvement in describing the transition to 1. Now you see, we wanted to fit an analytic function or a series to a function which has non-continuous derivative. And the Fourier transform of such a function is hardly converging because of this. So all what we are doing with this business of adding all the periodic orbits up to infinity is just to correct the smooth transition to transitions which are steps, but they are not interesting. So it is enough to look at the first three, in this case, the first two periodic orbits, the period 2 periodic orbits. But this shows you that the theory, I mean, all what I told you is not nonsense. It is okay. So what is the classical dynamics? The classical dynamics is given by the absolute value square. We spoke about it of U. And if you start with the eigenvector 1, this is the Peron-Frobenius article, then the probability will come to 1 eventually. And ergodicity means that you reach a complete equilibrium in phase space. So the butterfly finishes its action after some time and reaches there exponentially fast. Now, I want to tell you also something which you probably never heard about, and I didn't hear about it since 2 minutes ago. There is something which is called pseudo-Hermitian matrices. Anybody heard about it? So the matrix B, which we see here, is it is not Hermitian, but it is pseudo-Hermitian. And a pseudo-Hermitian is a different lecture. But it shows that this matrix has, as a consequence, it has a complex spectrum. But the amount of eigenvalues which become complex is bounded. So as a function of the parameter, we have a parameter lambda. So when you change the parameter, U has B has a real spectrum, and then suddenly there are pairs of complex conjugated values, and then there are very strange properties of the eigenvectors at these particular critical points. But then, after a while, you go to a domain where there are no complex. So this is, and it has many applications in physics, but I don't want to talk about it. Just to say that you heard something about it. Okay. So now we go to trajectories. After all, Lyapunov exponent is something of a trajectory. So what is a trajectory on a graph? It is the list of edges, right? You go from edge to edge to edge to edge, and you go from infinity to from minus infinity to plus infinity. However, the amount of symbols that we have, that is to say, the names of the edges is finite. And such problems have a name. It is called shifts of finite type in ergodic theory. And did any of you hear about the cat map? Or the maps, classical maps, chaotic maps. So Sinai, the great Sinai, have shown that if you have a classical of some kind, classical system of a kind which is going to ergodicity, then of this kind, for example, you can find a finite coding number, finite number of letters which encode all the possible trajectory. Now, not all of them are connected. You cannot go from any to any, but they are connected enough, like our graph. And the connectivity is what he calls the grammar, because you cannot put two letters one after the other if they are not within what the grammar allows. So then if you write all this as a sequence, then this sequence is a trajectory. Now, what is the Lyapunov exponent? I told you it's how trajectories separate, but you can look at it in a different way. You can ask what is the probability to remain on the chosen trajectory. So this is one minus the other. And the probability to remain along a trajectory is given by the probabilities of the product of the corresponding b's. And if you want to know how it behaves on in time, it is exponential, because all these numbers, all the b's must be less than 1 because their sum is 1. And therefore, you have a problem, a product, which finally goes to 0 if it is large enough. But you can also take the logarithm and you will get the Lyapunov exponent, which is the exponent. And this is what you do in ergodic theory. And then here it is written that the lambda is the Lyapunov exponent. The mean lambda is the limit 1 over t log p of xt of xi on the trajectory I. And then if you look at it in a different way, you can write it as a log of b's, as I showed you. Now, if you have a very long trajectory, then the probability to get a certain b is b itself, because there is a finite number of letters. Each letter has a probability which defines how much you can enter into this letter. So finally you get an expression which is written over the right-hand side on the top on this. So you take any initial edge, and then you compute the sum from all the degrees for the entire sum over the double index E, and you write b log b, the sum, and this is the Lyapunov exponent. This is a result from ergodic theory. Here, after I defined b, everything which I say also is precise. There is no approximation. This is the definition of a Lyapunov exponent: the probability to remain on the same, on a given trajectory per time. Now, why did I call it a mean? Because there are many trajectories. And what we did in order to get this result was to average over all of them. And this average tells you that the Lyapunov exponent is not a property of a single, but of the entire system. And then, there is a distribution. So if there is a distribution, you can also write the variance. You ask, what is the variance? Because it is distribution, right? So you have an expression, I don't want even to go, but there is an expression precise which defines to you the variance. Okay, this is the theory. So we have some time for examples. So suppose I take the adjacency matrix of the graph that we like, and I compute in this way the adjacent of these days, the Lyapunov exponent. So you see here the mean Lyapunov exponent as a function of the energy. And you see that if the degree of the graph is 2, so it's the linear graph, then it has very funny shape. If it is 3, if it is with triangular connection, then it is different. And then when you go to a higher and higher degree, then you see that finally you reach a certain limit, which means that the problem is self-averaging. So this is something which explains this figure, but I don't want to go into it. But do you know that? Did you ever hear about random matrix theory? Who did not hear about random matrix theory? Don't be ashamed. Okay. Random matrix theory is a theory which tells you that you can choose. Okay, you choose an ensemble of matrices, and you give the probability that each of the matrix, of the elements of the matrix will get a certain value. For example, you can take each ajj to be a Gaussian variable. Now, the classical random matrix ensemble is the one which is the Gaussian. All of them are Gaussian. So, and this is called the GOE, if the matrix is real, symmetric and real, and if it is imaginary, it is called GUE, unitary. And these are ensembles which are used usually because they have, first of all, you can compute a lot of things for them, and they are the most chaotic matrices which you can imagine. They have a certain distribution of spectral distribution, and their eigenspaces are unique, are filled. I mean, the eigenvectors are fill the sphere, the high-dimensional sphere, uniformly. So there is a uniformity of the distribution of eigenvalues, eigenfunctions, and a certain properties which are very well understood. These were defined many years ago by Wigner and Dyson and many others. So here you see the difference between the Lyapunov exponent, the mean Lyapunov exponent. Now the mean also includes averaging over the ensemble. The line with the red, I cannot show you, but the one which does not have a hole correspond to GOE and GUE. So these are the Wigner ensembles. There is another ensemble which is called G beta, never mind, and these have this spike in them. So you see that this is the Lyapunov exponent distinguishes between two different ensembles which have the same spectrum, by the way, but they have a different distribution of eigenvectors. So the Lyapunov can distinguish between these two. Let's forget about this. You can also write and show the connection between what we find here to the deregular graphs, but forget about it. Now you can look at the variance of the Lyapunov exponent, and here the story becomes unclear to us. We know what happens, but we don't have an explanation, and this is open questions. The distribution is very well defined. You see for different, but the disturbing part is that it decays like 1 over x to the 2 or to 3, which is not enough. You don't have enough decay fast enough to compute all the moments. So here are other examples that you see the same behavior. In the G beta E, the other ensemble, you have it also in the same way, but in some of them, you see that in the GOE, the power law goes to 3 asymptotically, numerically. And this is good because then you have at least a second moment, but not more. And this, in the other cases, it is going high, so then there is no problem. So that, okay, here, what we see is the variance for the other ensemble. And you see that it has a property that all these lines which you see on the left, which correspond to different sizes of the matrix, can scale down by a known formula which shows the curve. And the gray part is the domain of E for which the spectrum is complex. So you see that there is a different behavior of this property when you start to look when you look at the dependence of energy on the variance. Not explained. We did also some other examples, but this is of no use to you. And this is what to be done. So if you are excited by this new mechanism, you are most welcome to come to me and give you a problem. So there are models which use such measures to explain, for example, in cosmology, black holes. And this is the SYK model, which are given by matrices, which have no classical analog, because they correspond to spins. And a spin, half-half, the -1, +1, the ones of Dirac or Pauli, they are not classical. They correspond to h bar, angular momentum, which is h bar times half. This is very small. It cannot be smaller than that. So therefore, there is no semi-classical approximation, and then we are going to do it. Now the question is also how to include more quantum corrections, because we don't have here any quantum correction, any interference. The answer is very simple. We have the exact expression of the quantum mechanical evolution operator, U. If we take U cube, it is still a unitary matrix. But the product is a quantum product. So the phases on the level of three lines will be remained. But if U cube is unitary, then the B, which we generate by taking this U cube and generating the classical analog, will have all the properties which we need. So we'll have a Lyapunov exponent which contains inside it the quantum corrections. Not the entire, but the quantum corrections. And then also what is very much missing, but none of you is working in random matrix theory, is the question how to prove or how to verify analytically that what we have numerically is right or wrong. So this is what I wanted to tell you in short, and I thank you. Yeah. 50 minutes. Yeah, but then I did 51, so sorry.
That's okay, you had questions in the middle. So if you were on time, it was the people asking the questions.
So there are probably no questions because this is very new to you. Yes, please go ahead.
A little bit of a technical one. In this
but you see, I'm half deaf.
So sorry. In this wonderful trace formula asymptotics that you showed, it seemed that every other term was much more important. Like the second term was important, and the third term did almost nothing. The fourth term was important again.
Because it is the question of how many periodic orbits.
Yeah, so you have many just like this, right?
Well, you see that the point is that this was a D equals 3 graph, so it is with 3 connections. Now, in order to know how many periodic orbits you have to take A to the n trace of A to the n. A was the connectivity matrix, and to the power T, power n is right. And then you see that the number of periodic orbits goes exponentially. But until it starts to grow exponentially, it fluctuates. It depends on the structure, because there are many D equals 3 matrices. So therefore, it is not orderly. So
I was wondering if this comes from the fact that there are so many more even paths which just go back and forth once.
Yeah, but you see, the counting is not simple arithmetics. It is much more complicated arithmetics. And the simplest way to look at it is to say, okay, A has an has the largest eigenvalue, and this gives you the maximal growth rate. But then there are fluctuations. And they come because of the competition between what you said but you see, if you have squares, then you can also do like that. So you add more possibilities. You don't go only around the square. So you go 2 and 2. So you have 2 sources. And when you go higher and higher, you have more sources. And then there is a competition, finally wins the largest number. So
yeah, I think the way that I wanted to phrase my question is, if you take the obvious sources, for example, just going back and forth one edge, and can you speed up convergence of this asymptotic series in some sort of arithmetically simple way?
Well, here, yes, you see the green one. So the green is what we have for the smooth plus the periodic orbits of length 2. So you see, we miss the 1, we miss the 0, but we go very well along the part which grows. So, c'est la vie. Because you see, the energy dependence is coming, you see, through these factors which are ugly factors, which are the typical one is the arc cosinus, the argument of the arc cosinus. So they have the gamma. By the way, anybody of you mathematicians heard about Gershgobin theorem? The Russians. No? Yet? Yes? You know? So you come to get not ice cream, but cake also. So Gershgorin said a very interesting theorem, very simple. He says, suppose that you have a matrix, and suppose that you want to have an estimate to know where will be its eigenvalues. And let us say it is a Hermitian matrix, but he proved it for a general matrix. Then he says, take each row of the matrix, extract out of it the diagonal, and put the value of the diagonal on the line. Then take the sum of the absolute values of the off-diagonal elements for each line, and make a circle around the diagonal one with this radius. And then look at all of them. Now, the theorem says that the spectrum must lie in the union of all these circles. And if the circles are separated, then you know that you are that where to find. If you find n circles which are not, then you know that. Now, if you start with a diagonal matrix, so you only have the diagonal elements, so you know where the centers are, and you know that the radius are 0. So you have diagonal. So Gershgorin is right. But if you start to have some perturbation which makes the off-diagonal slightly larger, then you'll see how the radius grows. And you know that when the radii will touch each other, you start to be in a problem, because then you have avoided crossings and all the kind of things. But otherwise, so this, by some miracle, this appears in our theory. And the theory is the one I told you about, how to write a matrix like a unitary operator, really a Hermitian matrix, like in its analog of a unitary operator. And it appears there, and that's how I learned about it. But nobody knows. Mr. Gershgorin also died at the age of 33. So he had one theorem to his name, which is very famous. Good.
Okay, so it sounds like we may have another seminar happening now, so let's thank you. Uzy again.